This section is about patterns of chemical behaviour. It covers higher tier topics in chemical reactions and in energy transfers. First, more about chemical reactions. In the foundation programme, we saw that neutralisation is the reaction between acids and alkalis, in which an alkali neutralises an acid to produce a salt and water. For the higher tier, you need to know a bit more about this. It's important to know the difference between dilute and concentrated acids and alkalis, and strong and weak acids and alkalis. Dilute and concentrated are measures of the amount of water added to the acid or alkali. The more water added, the more dilute it is, just like diluting orange squash. Strong and weak are measures of the number of ions produced in water. When acids or alkalis are added to water, they produce ions. Acids produce positively charged hydrogen ions, H+, and alkalis produce negatively charged hydroxide ions, OH-. In a neutralisation reaction, it's the positive hydrogen ions from the acid and the negative hydroxide ions from the alkali that combine to produce neutrally charged water. So strong and weak acids have more or less H+ ions, and strong and weak alkalis have more or less OH- ions. So a strong acid like hydrochloric acid produces many hydrogen ions, and a weak acid like citric acid produces few hydrogen ions. A strong alkali like sodium hydroxide produces many hydroxide ions, while a weak alkali like sodium bicarbonate produces a few. That's the end of the higher tier section on chemical reactions. Next, some more about energy transfers in reactions. Most chemical reactions become hotter or colder as they proceed. They give out or absorb heat because of the making and breaking of chemical bonds. Making chemical bonds gives out or releases energy. It's called an exothermic reaction. Breaking chemical bonds requires energy. It's called an endothermic reaction. You often need to supply energy as heat to break chemical bonds and to start a chemical reaction. Watch this clip and think about the different energy changes that are taking place in exothermic reactions.
This is a strip of magnesium metal. Drop it into hydrochloric acid and watch using a heat-sensitive camera. Blue is cold, purple is warm, yellow is hot, white is even hotter. Clearly the reaction releases heat. It's exothermic. You don't even need solid chemicals for an exothermic reaction. The water in this beaker is at room temperature, but add another cold, clear liquid and a bubbling reaction starts immediately. The heat-sensitive camera reveals gas being given off. It shows up because it's hot. The heat seems to come from nowhere, but actually it was locked up in the chemicals all along. Chemists show what's going on in an energy level diagram. Imagine this ball represents the reactants, the chemicals that go in to start the reaction. Before they start reacting, there's this much energy in them. As the reaction begins, it starts to make new chemicals, products plus heat. The products only lock up this much energy because some of the energy that was in the reactants has been given out to the surroundings as heat. Exothermic reactions always work like this. The products have less energy than the reactants, so the energy left over heats up the surroundings.
But most exothermic reactions need something to get them started, like rocket fuel.
Mixed together, nothing happens. Like a lot of chemical reactions, they need a little help to get started. Add a little energy. Rocket fuel needs a bit of heat energy to light the fire of the big reaction. Again, an energy level diagram shows what's going on. Overall, this is an exothermic reaction. So the reactants have more energy than the products. But this time, before the reaction can start, there's a barrier to overcome. It needs a little extra energy from outside to kick the reactants over the top of the energy barrier before the reaction will go. The amount of energy it takes to get going is called the activation energy. Provide that, and the reaction makes it over the barrier and products can start forming. Once it starts, there's no going back.
So, in an exothermic reaction, more energy is released by the reactants than is needed to chemically bond the products. This excess energy is given off as heat. Some heat input is often needed to introduce activation energy to start off the exothermic reaction. Once the reaction starts, heat from the reaction itself then provides the energy to keep the reaction going. But what's going on inside the actual atoms? Let's look at the exothermic reaction when natural gas burns in air.
Natural gas is methane. It's made from one carbon atom bonded to 4 hydrogen atoms. The bonds are forces that attract the atoms to each other. They don't want to let go, but when the heat comes on, things start to change. Heat provides energy to break the bonds, not just in the methane, but in the air around it too. Eventually, the methane molecule does split apart. Meanwhile, oxygen molecules in the air are also split apart by heat. Once that's done, the atoms are free to form new bonds. Forming new bonds makes the reaction products, water and carbon dioxide. But those molecules don't need all the energy that their individual atoms had when they were free. So making bonds releases energy. If making the bonds in the products releases more energy than it took to break the bonds in the reactants, the spare energy comes out as heat. Overall, the reaction is exothermic.
An endothermic reaction is the opposite of an exothermic reaction. It absorbs heat. Like an instant ice pack.
Inside the pack are dry ammonium nitrate crystals and a small bag of water. Break the bag open and the reaction starts. The heat-sensitive camera shows the water as yellow. It's quite warm. Black shows where the mixture is much colder, as the endothermic reaction between ammonium nitrate and water takes heat out of the beaker. Quickly, it's down to just 5 Celsius, as cold as a fridge. Again, an energy level diagram shows why. Remember, in exothermic reactions, there's more energy in the reactants than there is in the products. Overall, heat energy is given out when the reaction goes ahead. But in endothermic reactions, it's the other way round. The reactants have less energy than the products. That means the reactants have a huge energy hill to climb for the reaction to go ahead. They must steal the energy they need from the surroundings. That's why the temperature drops.
So, in an endothermic reaction, more energy is needed to chemically bond the products than is released by breaking the bonds of the reactants. This energy shortage is taken in as heat from the surroundings. This creates the cooling effect. Here's a higher tier question about energy transfers in reactions. Methane burns in oxygen to form carbon dioxide and water. The energy needed to make or break the various bonds is listed. How much energy is needed to break a mole of methane into atoms? There are 4 CH bonds in methane. The bond energy for one CH bond is 435 kilojoules, so the bond energy for 4 CH bonds is 435 times 4, that's 1740 kilojoules. How much energy is needed to break the oxygen bonds in the reactants into atoms? There are 2 moles of oxygen molecules. The bond energy for one OO double bond is 498 kilojoules. So multiply this by 2 to give the correct answer, 996 kilojoules. What energy is needed to break all the bonds in the reactants, methane and oxygen? Four CH bonds equals 1740 kilojoules, and 2 OO double bonds equals 996 kilojoules. Added together, that's 2736 kilojoules. What energy is given out when new bonds are formed in the products, carbon dioxide and water? Two oxygen-carbon double bonds are 805 times 2 equals 1610 kilojoules, and 4 OH bonds are 464 times 4 equals 1856 kilojoules. Added together, that's 3466 kilojoules. How much energy is absorbed or released when the reaction occurs? In this reaction, more energy is released in making the bonds in the products, 3466 kilojoules, than is used to break the bonds in the reactants, 2736 kilojoules. So the reaction is exothermic, it gives out heat. The amount of excess energy released for each mole of reactants is 3466 minus 2736 equals 730 kilojoules. That's the end of the higher tier section on chemistry.